Okay, so when we think about applying our knowledge in robotics for any engineering solution, especially if we are looking in more futuristic stuff related to smart city, uh, we need to have a comprehensive understanding of what robotics or what a robot is capable of doing. Okay, so there are a few um, aspects that we look at. For a robot, they should be able to sense and act on the environment. Okay, so control will be involved. Okay, with certain level of perception, being able to understand what is happening in the surrounding. So that should be sensing, action, control, and intelligence, right, related to robotics. Okay, so by the end of this course, you should be having a good concept of how they are related to each other. So we will start off by looking at robot mechanics, right? So meaning being able to represent the robot, all right? We need to be able to um, represent the robot in a systematic and mathematical way where we can analyze them and then being able to understand its interaction with the environment dynamics, okay? So this involves a lot of physics and spatial representation, all right? And finally, we will design control system that will be able to achieve a desired outcome, okay? The state of the robot that we want by generating the right control input. Okay, so in this afternoon lecture, we will actually go deeper into control system design. Okay, the idea or control problem is really to be able to achieve a certain desired outcome that we want by sending in the right control input. Okay, so there are some performance specification when we are doing the control system design. And this course or this morning's lecture, we're going to also look at planning system, right? In control, we kind of assume that we know what we want to achieve. But really, to move from an initial state to a final configuration or a final goal, right? You need to do a sequence of action. Okay, so that part in telling the robot what kind of action to take eventually to lead from a starting point to a goal point is really a planning system. And of course, understanding the environment is important. So perception is important, right? But in this course, we're going to take a quick look at vision system, right? Of course, there are a lot other way of understanding the environment. It could be haptic, that means a force feedback from the environment. It could be acoustic, from sound wave, or even thermal, other form of energy source to sense the surrounding. All right. Okay. So just to give you some illustration of this entire knowledge structure that we are building with robotics. Imagine if you want to achieve certain things, like doing a mission here for the robot to take the water to help this dying tortoise. Okay, so it will need to be able to understand that, okay, assess the situation, and there will be control required to tell the robot to send in the right input for the robot to do the right thing. Okay, and of course, planning to achieve this goal eventually, right? Okay, so we always start off with modeling the system. Okay, so this part here is kind of like representing our robotic system. Okay, being able to represent it is the first important part, right? And then we are able to design control system and come out with the right planning algorithm to achieve what we want. All right, so in this lecture, we're going to cover a few things, starting from overview of robotics and then to spatial representation, meaning how do we actually geometrically model this robot, really the kinematics of our robot system. Okay, so in fact, robot mechanics kind of consists of three main parts: kinematics, static, and dynamics, right? So mechanics is the branch of physics where we are interested in the motion of moving body, uh, including the cause of this motion, meaning the force or the torque that causes this motion. Okay, and then quick look at dynamics, control, and planning, and then robot vision, how robot understand the environment. Okay, we start off with something simple. Okay, ask ourselves what is robotics. So this will kind of help us formulate the scope that we are dealing with. Okay, so we need to help our friend out in answering the question of what is a robot. Okay, so what do you think a robot is? Of course, there is actually no strict definition or no agreeing definition on what a robot is. But in this case, most of the time we are looking at a design machine that is there to achieve certain mechanical tasks while interacting with the environment. Okay, so in the pop culture, you see some movies about robots. Okay, they could be something that can reconfigure themselves or to suit very different environment or to look very differently or do different tasks like flying, transporting stuff. And of course, there are some robots that take human form, okay, social robotics, etc. Okay, more futuristic in the research area. Sometimes they are interested in having the robot to go into the body to do certain part. In this case, a nanobot that can repair the red blood cell. Right? But of course, they don't just exist in the fictional world. Okay, in real life, we see robots. They are also either working alongside human beings or living together with us. Okay, we have social robots that look like human, taking the form of human. Okay, we have a bipedal robot with 2 legs. We have legged robot. Okay, 4-legged robot or quadrupedal robot. All right, and I'm sure many of you have seen this vacuum robot. Okay, that help us clean the floor, right? And in the industry or for automation stuff, okay, we have manipulator arm that can move things from one place to another very quickly or do heavy duty stuff. Right? There are also surgical robots that can perform surgery. Okay, I'm not sure if you can see this. Yeah, it's a bit laggy. Yeah, but there are robots that can do very intricate motion going into the body. That's not. Yeah, this is a bit laggy. Okay. So we see that robot can take very different form. Of course, the reason why we have many different kind of robot or different kinds of robot or different form is that we need them to do different work, different kind of tasks, and in different environment, right? So you will see robot covering a whole range of different um, configuration of types like flying robot with drones. And we could also have this kind of multi-linkages, snake robot, continuum robot, and we can also have fish robot. Or manipulator arm is something that we see very often, right, in the industry automation. Okay. So our scope here about robot is based on the definition that robots are machines designed to complete mechanical tasks while interacting with the environment. All right, so kind of like having 3 aspects. They should be artificially designed and they are there to do mechanical tasks while interacting with the environment. Okay, so things like computer software or sometimes what they call the bots. Okay, although they are able to complete certain tasks, okay, but they are not robot because they don't do mechanical tasks. Okay, when we talk about mechanical tasks, we are talking about having certain motion. Okay, either moving something from point A to point B, okay, or moving itself from point A to point B, right, while interacting with the environment. Of course, other living creatures like cats and dogs, they could also do something like this, but they are not machine designed. Okay, so we are talking about design machine. Right? And another useful definition is that this robot should be able to sense, perceive, plan, and act in a physical environment, right? At different level of autonomy. Okay, so sometimes robot can do something independently, totally. Okay, sometimes it does something with the guidance of human, and sometimes it is used to collaborate with human. Okay, so at different level of autonomy, right? So the scope will really cover kinematics when we talk about robotics, and control part where we have sensing, actuation, and control, and finally planning and perception. Okay? So if we look at one example, okay, we are talking about machine that is designed to complete mechanical tasks or interacting with the environment. So there will be this agent that is moving around in the environment, right? And a specific task is to serve the this customer, or either bring something to the customer or take something from the customer, okay? And it is interacting with the environment, all right? So this will kind of form the loop. So we have this whole big picture. The first part is to be able to represent the robot, right? Because your machine only understand mathematics and science. I mean physics, how you represent the physics based on mathematics. So this part here is the first part that we're going to look at, okay? Being able to represent the robot mathematically. Okay, so we look at mechanics, and for those who have done physics, you know that mechanics is this branch of physics that deal with the motion, okay, of something, right? So if we are talking about kinematics, we are looking at just motion, the geometry, without thinking about the forces. Okay, so we don't care if we are not concerned about force acting on that body. We are just concerned how the body, okay, or the configuration of this particular body. And static is actually when we don't care about how the thing moves, because the thing is in equilibrium most of the time in a static state. And we are only concerned about the force interacting between the bodies. And finally, dynamics is when we are really concerned about the forces that is acting on this body. Okay. Sorry, I think there's a typo in this. This should actually be static and this should be dynamic. Okay, so these two are swapped. I think there's a misplacement here. Okay. But anyway, the first part is to be able to describe the robot in a systematic or mathematical way. So that is actually starting off from spatial representation and transformation. Actually, this part is not just useful in robotics, being able to systematically describe something in 3D space and how you transform something mathematically. This is also important if you're dealing with things like computer graphics and even computer vision. Okay, so I think you might already have your lectures on computer vision that is focusing more on the intelligent part of making sense of the images. Okay, but in robotics, we are interested in using these images to help the robot understand what is happening in the surrounding. Okay. So we have to start off with coordinate system as the basic or the fundamental way where we start to describe uh, something. We use coordinate system. So everyday example of coordinate system. Okay, if you play with board games, okay, when I want to describe a certain pieces, where is the position of this piece, we need to have some form of indexing, right? We can talk about the row and the column. Okay, for those who play with the game of Go, okay, you know that you can define which row, which column. Okay, and in chess, right, maybe the column is represented by alphabetic alphabets, and then the number for the row. Okay, so you can define the pieces position. Okay, so there are also three dimensional coordinates, okay? Not just the XY, but also the Z or the layer, right? And there are sometimes 2.5 not truly three-dimensional, but it gives you 3D information as well. So all these contour, they have values telling you the height or the altitude of the ground, okay? And they are also spatial, or rather this celestial map, the sky map, okay? Taking references from different position in the sky, all right? So there are a few ways of representing mathematically the coordinate system, right? Cartesian coordinate is something that um, we are all very familiar with, X, Y, Z, okay? So Rene Descartes actually realized that it's very convenient to describe the position, okay, for something in 3D space using X, Y, Z. Okay, so X, Y, Z is nothing but the distance away from the three axes, okay? How far is it away from the origin in the X direction, in the Y direction, and Z direction? Okay, so there's this Cartesian coordinate. So there are also spherical coordinates, okay? You see things like using r, theta, and phi. That means the angle, which direction is it facing, and the range or the distance away from the origin. Okay, and we have also cylindrical coordinate system. All right. So in this course, something new is homogeneous coordinate system. Okay, so for those who haven't done robotics, if this is the first time you see this, you might need to pay a little bit of attention to homogeneous coordinate system. Okay, it will be the kind of like a foundation for you to describe any rigid body or reference frame in 3D space. And then projective coordinates is also important, but for those who are doing robot vision or computer vision photogrammetry, okay, this part or computer graphics, okay, so this part will be something that is very important. Actually, it's an extension of homogeneous coordinate system. So we're going to go into detail later on in looking at this. All right. So later in robot vision, this projective coordinate will be important. Okay, let's start off with something very basic on frames. Okay, reference frames. So when we want to describe a rigid body in space, okay, we can attach what we call frame to this rigid body. Right. So a frame that is attached to a rigid body will have orientation and position. Right. So now you need to, let's say I want to describe this orange block here. Okay, the pose of this orange block. We need to tell someone the position and the direction, right? So how do we do that? We can stick a rigid frame onto this body, okay, so that we can describe this, all right? So this is something very useful. Okay, so reference frame can be attached to rigid body. Let's say we have a satellite that can take the position of, let's say, the aircraft, okay, or the radar, right? So we want to be able to describe them, so we can stick reference frame onto them, right? So now I'm able to describe the pose of, say, for example, A, the pose of A with respect to C. Okay, so let's say this CTA. Sorry, my laptop is down, so I'm using this where I cannot really write. So the writing will be slightly slower. Okay, so when we use this notation, what we are saying is that we are describing A, okay, the position and orientation of A, looking from C, okay, observing from C. Okay, so usually you will see textbook using this notation. The subscript is the one that is being observed, okay, in this case, frame A, and C, the superscript, will be the observer point of view, okay? So this transformation matrix here, T, we use T to represent. Okay, this transformation matrix T is really describing this A with respect to C. Okay, so let's say if I'm interested in the position of A with respect to the origin 0, okay, frame 0, right? And I have this information of my origin, okay, to my C frame, okay, and I want to really find OTA. So I can actually use a method, this matrix multiplication, okay, to get this result. Okay, so it's like vector addition. I'm sure you guys did vector addition even in your high school time. Let's say I want to find vector AB. Okay, right? I can actually take A0 plus B0B, right? I can do that. Okay, so that is simple vector summation, but it is very convenient if we use this matrix multiplication. Later on, we will look at this. This is actually what we call homogeneous transformation matrix. Okay, so this T is homogeneous transformation matrix. Right, just give you a heads up that we are now able to, if we have all this information, we can change this observer from one point to another. Okay. So when we talk about spatial description, when we want to describe the spatial information of something, we want to be able to define the position and orientation with respect to a frame of reference. Okay, that means frame of reference is always the observer being in somewhere, right? Okay, so this will involve two things, right? Let's say if I want to describe the position and orientation of something, it is always using a vector to represent the position. Not always, but a lot of time we can use vector to represent the position. Okay, and we can use matrix to represent the orientation, right? We can use matrix to represent the orientation. Okay, so vector to represent position, very straightforward. Okay, we just give the Cartesian coordinates. Okay, so if we are interested in this point P here, okay, observing from frame A, okay, we just write down the distance away from the origin in the X, Y, Z direction. Okay, so if I want to describe the position of my friend in front of me, okay, I tell you how many steps to my right and how many steps forward in order for me to reach him. Okay, so that is like his position, right? And in homogeneous coordinate system, okay, it's actually in this course you just need to know you will add a 1 at the bottom. Okay, so instead of just writing X, Y, Z, you put a 1 at the bottom. Okay, so for those who eventually do things like computer graphics, right, you will know that this is a form of projective coordinates where 1 is the scale, okay, but we won't go into detail on this right now. Okay. So how do we actually represent the orientation? That is something slightly less common, right? So if this is the first time you do robotics, you may not have used a matrix to represent orientation. Okay, but maybe in your high school days, you may have represent rotation and things like that using matrix. Right? If you can still remember how you rotate something on a 2D plane using a rotation matrix. Okay. In 3D, you can represent the orientation, right? By using a rotation matrix. So this part here is actually a rotation matrix. Okay. Let me see if I can use the whiteboard for this. I will not be able to see. So let me try to see. Let's take this off. Okay, in case I need to write, because my laptop is down, I cannot use a touch screen. So maybe I will need a whiteboard to very quickly show you this. For those parts, I hope you guys on the right side can be on the, I think it's fine, okay? I will let that down after I do this writing in tense part here. Okay, so how do we represent this orientation? It's actually quite straightforward, right? If we have this frame here, let's say A frame is absolute frame, okay? We want to describe another frame B, okay, with respect to A, okay? So for me to be able to do that, okay, I need to have these three vectors, XB, YB, and ZB, okay? So it's nothing but, if I want to write down my orientation of B with respect to A, is writing these three vectors down. Okay. So this is a 3 by 3 matrix with three vectors. Okay, so this part here, okay, this column here is actually a vector, and this column here is another vector in the y direction. All right. So let me. So this is one vector. I will use a different color for this. This is another vector. And this is the third. Okay. So this is your z vector. And this is your y vector and your a vector. Okay. So once you get this part, right, the next, the rest of the stuff will be quite straightforward. Okay, for those who are on my left side, you may not be able to see. Okay, let's this. Okay, so this part here, I know if this is the first time you see this, the dot product may be a bit confusing, but if you still remember, dot product is nothing but a projection of a vector. So scary. Okay, it's nothing but a vector that a projection of a vector. That means if I want to project this vector z, zb onto this axis of A, okay, you can do a dot product. All right. This one you might need to take some time to digest. Okay, but don't worry too much. What we are saying here is that if I want to describe B, okay, if I want to describe B with respect to A, that means looking from A, right, the orientation, I can use a 3 by 3 matrix that consists of three vectors. Okay, so one vector is the vector of XB looking from A, and YB looking from A, and ZB looking from A. So these three vectors will form my rotation matrix. All right. So for those who haven't seen this before, haven't taken the course on robotics, okay, you will take some time. For those who have taken robotics, okay, you should actually find this very straightforward. All right. So let's go down to two-dimensional problem to illustrate this very easily. Okay. Let's say if we are just looking at a plate, this is frame B. We want to describe B with respect to A. Okay. And so now you only need to define two vectors, right? You only need to define two vectors. This IB and JB. Okay. So this is IB, right? This vector here is IB and this is JB. Okay. So what do you think it's IB? The vector IB here. If you use simple trigonometry, all these, for example, are unit vectors, unit of one. Okay. So what is vector? Should be. Anyone want to give a guess? If this is theta, this angle here is theta. So what is the coordinate of this? This is actually IB, okay? As I write, you can slowly think. This part here is actually IB. And this part here is JB. Sorry for the handwriting. Because I think my laptop is gonna work. Okay. So IB is nothing but if you write down the coordinate system of IB, it should be the distance from the origin in this direction is cosine theta, right? Okay, I will just use C theta. Okay. And the distance in this direction, okay, in this the distance here, this is sine theta, right? So now you have sine theta. S theta means sine theta, okay? I use a short. Okay, so now I show you this IB. What about JB? Do you think you can now tell me what is JB? What is the coordinate of JB? What is the length here? This is theta. So this will be theta. So what is the length? Is it sine theta? Sine theta? Okay, yeah, almost correct. But remember, it's in the negative direction, okay? So you need to put negative, correct? Negative sine theta. Okay, and what about the height here? Now no more. Okay, what is the height? Cosine theta, correct? Okay, so now you can show that maybe in your secondary school day or in your high school day, you already know this rotation matrix. But now using this vector method, you can also show that the rotation matrix is actually cosine theta, sine theta, negative sine theta. Okay. So in other words, what we are saying is that when you want to describe B from someone standing at frame A, the orientation, okay, you can use this matrix here. All right. You can use this matrix, this part here. Okay. So of course, this can be generalized to three-dimensional space, but I'm showing you 2D to make it simpler. Okay. To give you some understanding of the concept, checking yourself, understand. If you just look at something like this, okay, what is the position vector of B in A? What is this point here? If you're someone standing on A, right? You need to count the distance, right? 1, 2, 3, 4, 5. So it should be 5. right? The first coordinate is 5. And how far is it on the vertical? 1, 2, 3. Okay, so the second part is 3. Okay. All right. And then what about orientation? What do you think is the orientation of B in A? Okay, let's start off with the first vector xb here. Okay, so this part is actually vector xb. So how will you describe xb if you are someone standing on A? What is the coordinate? Should be anyone want to shout out the answer? Yeah, I do the first one for you. It should be 0, 1, right? This vector is 0, 1. Okay, because it's in the y direction 0, 1. So what about this vector? Anyone want to shout out the answer? Minus 1, 0. That's correct. Okay. So now you can have this orientation. Right? Very good. So if you use trigonometrical functions, let's say you say that this is 90 degrees, okay, and you use the formula earlier on, okay, this formula, you substitute 90 degrees. So cosine 90 is 0, right? And sine 90 is 1, okay? And so if you substitute, you will also have 0, 1, minus 1, 0, okay? So that means you can use a formula as well, okay? If theta is 90 degrees, this is the same as theta being 90. All right? So now it becomes very straightforward. Okay, so this part I'm going to go slightly faster, okay? Spatial transformation is actually the same thing as spatial representation. When you want to describe someone's pose, someone's position and orientation, it's the same as you moving from your point of observation to the person, okay? So if I say my friend is like 2 meter or 2 steps to my right and 3 steps in front of me, okay, that is his position. It is also the same as I need to transform myself to him by moving 2 steps to my left and moving 3 steps in front of me, okay? So this transformation is the same as representation. Because there is a fanciful name like duality for this, right? But it is really just quite intuitive. Okay, so the same thing you can apply this on for describing transformation. Okay, if I'm someone A, I rotate myself by theta degree, what will I become? Okay, I can use this rotation matrix. Okay, that's why you can do this 2D rotation, okay, using this matrix. So if I have a vector, I multiply by this rotation matrix, I will get the new rotated vector. Okay. So this actually allow us to change the coordinates of a position vector. Okay, so initially, let's say if there's a point P, okay, this point P, and someone standing observing this P. Someone motion of P, but he can ask the person on B to tell him why is BP, okay? And if he knows his orientation, okay, A and B, okay, he can find out by using this transformation or this multiplication, okay? Right? So this will give you the position of P in coordinate frame A. All right, so this is something useful. Okay, so this part I will leave you to take a look at them yourself the derivation, okay, which is kind of straightforward. Okay, if you want to do an offset, shifting it a little bit, you'll realize that, okay, it is nothing but this changing it to A first, and then doing a summation, a vector sum A TB. Okay. So now instead of writing this part here, of course we can just write this operation. Okay. So what is the idea here? Let's say this part here is that, let's say you have a sensor on frame B. Okay, you use a sensor on frame B, and then you are able to observe the position of this P. Okay, but you are interested in P from A. Okay, you are interested in finding the position of P from coordinate A, coordinate system A. So how do you do that? You can actually use a sensor to measure and get this position P with respect to B. And using the relationship of the sensor with respect to A, okay, then you can work out this new value that you want, okay, which is the position of P with respect to A. So doing this, you need two operations. You need to do a matrix multiplication, and you need to do a vector summation, right? That means a multiplication and a plus or summation operation. So we are going to introduce you with something that is more straightforward. You just need to do one matrix multiplication, okay, using what we call homogeneous transformation matrix. Okay. So this homogeneous transformation matrix is a 4x4 matrix, okay, which consists of the rotation matrix and the position vector of the origin of B with respect to A. And the last row, okay, the last row, you just need to put 0, 0, 0, 1, okay? So that it becomes 4x4, okay? So this part here is 3x3. This is 3x1, okay? So all this part here is 3x4, and you have one more row, so it becomes 4x4. Okay, so your transformation matrix is 4x4. Your homogeneous transformation matrix is 4x4. All right. So from now on, you can just do one simple operation here. Okay. Yes. You can just do one simple operation. Okay. Like this here. Okay. Without having to do two operations. Okay. So now the key becomes finding out what ATB is, right? This transformation matrix. Okay. So this part here will be like your fundamentals for working out spatial transformation, okay? Or being able to represent this spatial information of a point or a body. Okay. So now we summarize a bit of the key points. You are able to use homogeneous coordinates to do spatial representation and transformation, okay, of the pose or the transformation actually. Right, so this involves using nothing but this homogeneous transformation matrix, which consists of a rotation vector, a rotation matrix, and a position vector of the origin. Okay. So now this composite transformation matrix is important. Okay. If I want to find something, let's say from 0 to n, okay, but I only have information of 1 to 2, 2 to 3, 3 to 4, and all the way n minus 1 to n. So how do I get 0 to n? Okay, I just do this matrix multiplication. Okay, so if you have a robot with a lot of linkages, okay, each of these join can give you a reading from one link to another. So link I to I plus 1. So if you have link I to I plus 1, and you are interested in finding link 0 to n, meaning from the 0 to the ripple or the n effector, you just need to multiply all this that you have. Okay? Right? So in the interest of time, I won't go through this example, but it is in your slide. So try to test yourself if you are able to work out this with the numerical substitutions, okay, with all the values. So remember earlier on Q1 plus 1.1, we did something like this. Okay, so now you should use matrix multiplication to help you find ATB. Okay, so make sure you try this out on your own. Okay, I won't go into detail. Also because my writing is not possible without my laptop now. Okay, and if we look at this orthogonal matrix that we have talked about, right? Back to this 3D rotation matrix. When we want to define this orientation of something in 3D space, the best way of, there are actually a few ways, okay? You can use rotation matrix, you can use rotation vector. Okay, some of you may know about quaternion. Okay, there are many ways. So let's say we use rotation matrix. But one common way of describing is to say how much you rotate in each of these axes, right? So if I want to describe the orientation of this rigid body here, for example, okay, I say I rotate it how much in the X direction, how much in the Y direction, and how much in the Z direction. Okay, so I can have these three numbers, right, to represent my orientation. We actually call this Euler angles. Okay, so in the aeronautical industry, they do a lot of they use this convention a lot. Okay, I can't really draw. Let's say you have a plane, right? So you want to describe the orientation of this plane. I'll use another chart. Okay, you can describe this plane using what they call roll pitch yaw. I'm sure you guys have heard of this, right? Roll pitch yaw. Okay, so basically roll pitch yaw is nothing but the rotation in these three axes. Okay, a combination of the rotation in these three axes. Right? Let me use a different color. Okay, so let's say we have rho should be alpha, pitch, beta, and yaw gamma. Okay, so you are describing alpha, beta, gamma degree in all these three axes. Okay, so this is nothing but multiplying three rotation, right? Three rotation matrix. So you can have this kind of formula. Okay, so this is actually very common in your textbook. You will have, there are like 24 different combinations depending on the order. Okay, so one important thing I need to kind of let you know is that rotation matrix, the product of rotation matrix, they are not commutative in general. Okay, that means the order matters. Whether I rotate first in the x-axis, then I rotate in the y-axis, is not the same as me rotating first in the y, then x. Okay, the order is important, right? They will be different if you do a different order. Okay, that is in general. Okay, so when do you think they will be the same? Is there a situation where rotation matrix is commutative? So if you think about a rotation on a plane, okay, let's say I have a vacuum robot. I rotate the robot on the plane. That means a robot cannot fly, cannot flip or anything. It can only rotate on the plane and move on the plane, of course, right? When that happens, your rotation is commutative. Okay, whether you do a anti-clockwise 60 degree, then a clockwise 90 degree, is the same as you do the clockwise 90 degree first, then anti-clockwise 60 degrees. Okay? That means it's like minus 60 plus 90 is the same as 90 minus 60. That is only for 2D rotation. Okay, it's commutative. But for 3D, make sure you be careful. Okay, the order of your rotation is important. Okay, so that means when you do this kind of problem, you need to make sure that you are using the right convention. There are different conventions. Okay, usually they use row pitch, your X, Y, Z rotation about X, Y, and then Z. Okay. Okay, again, I will leave you to look at this at your own time. Okay, test yourself if you know this, why is this rotation about x-axis and why is this about y-axis and z-axis, so on and so forth. Yeah, you should be able to answer this question, okay, if you understand what is this. So let's very quickly check if I'm rotating theta degree in the anti-clockwise direction, right? So which of the following do you think is the right rotation matrix to represent? Who think is 1? Who think is 2? Who think is 3? Okay, you all think there's a trick, is it? Okay, so anti-clockwise theta degree, okay, in the x-axis, you need to be careful. So this matrix multiplied by any vector, okay, if you rotate something in the x direction, your x coordinate will not change. Okay, so for your x coordinate to not change, okay, only this matrix is possible. Okay, right? Okay, let me. So if you look at this part here, 1, 0, 0. So whatever matrix, if you multiply by x, y, z, okay, your x will still be x multiplied by 1. Okay, so this is rotation about your y-axis, and this is rotation about your z-axis. Okay, so this part, if you understand, or you can get it right, that means you already understand this rotation matrix well enough. All right, so inverse transformation, no big deal about this. It's just if I want to get the position of B with respect to A, okay, it's the same as I inverse the position of A with respect to B. Okay, meaning if I want to describe my friend position with respect to me, it's the same as inverting my position with respect to his. Okay, so that is inverse. But the good thing here is that you can apply this formula. Okay, you don't need to use the usual way like getting your adjunct matrix, find the determinant, etc. For a special property here, you just need to get the transpose of your rotation, and then this multiplication of your transpose of rotation by the position vector and add a negative sign. Okay, a lot of people will just add negative sign here, which is not correct. Okay, you need to multiply by the inverse of rotation. Okay, anyone can tell me what is the special meaning of rotation transpose? Is there any special thing about doing a transpose of our rotation? So transpose is nothing but changing row to column, column to row. So there's a very special property about your rotation matrix. Or maybe I will change the question. How do I get the inverse of my rotation? Anyone want to guess? Inverse of my rotation is the transpose of rotation. They are the same thing. Okay, that means you don't need to do a proper inverse of this matrix, find the determinant, find the adjunct matrix, etc. You just need to change the row to column, column to row. Okay, that's a special property of rotation matrix, which is an orthogonal unit matrix. But I won't go into detail for this, okay? If you are doing a full course on robotics, you will probably look into this. But for now, you just need to know for the inverse of rotation is just a transpose. It's the same as a transpose. Okay, so just change row to column, column to row. okay, or just apply this formula that you see in this slide here. And you can easily find your inverse of your transformation matrix. Okay. So now we finish spatial representation, which is the foundation. So the rest of it will be very straightforward. Okay, the mechanics, really the kinematics left. So when we talk about manipulator kinematics, we are just talking about this configuration most of the time. Some terminology, okay, the base will be something that's attached to the ground that will not move, okay? And then the end effector is usually the point where it is holding on to a tool. That means a gripper, okay? Most of the time, that is the end effector. And then joints are part where it connects two links, okay? So these links are the moving bodies of your robot arm or manipulator, okay? So when we talk about degree of freedom, a lot of time in this system of manipulator arm, okay, we actually talk about how many joint variables do we have. So in most of the course, each of the joint will only have 1 degree of freedom. Okay, so if you have a 3-joint robot, there will be 3 degrees of freedom. All right, for this case. Okay. So in what you see here, this is a what we call triple R serial arm, revolute, revolute, revolute. That means 3 rotational arm. Okay, so there will be 3 degree of freedom. But of course, it can get a bit more complicated when we are looking at the task space. Okay, so let's say there's a constraint. Okay, this robot is constrained here. So if you want to describe the configuration, in this case, you want to describe a configuration, you just need 3 numbers, right? 3 variables. The joint variable Q1, Q2, and Q3, for example, or theta 1, theta 2, and theta 3. Okay. But if you look at a constraint like this, okay, in this case, to describe this robot, you actually only need 1 numbers, right? It is only varying in this, along this X direction, okay? So be careful whether you are defining it in your configuration space or in the task space, etc. So we see a lot of mechanism that looks something like this, even though there are 3 joints, but really the robot is only doing a 1 degree of freedom in the task space. Okay, so this quiz, you can take a look at them yourself to test your understanding, right? The number of DOF or degree of freedom when we are talking all these different joints, right? So usually in most robotics course, you will only be looking at revolute joint and prismatic joint. Okay, meaning there will only be 1 degree of freedom. So revolute joint is nothing but rotational joint. That means it can only rotate. Prismatic joint is translational joint. It can only translate. All right, move up and down or forward and backward. Okay, cylindrical. Okay, meaning it can rotate and translate. Okay, planar, it can only translate, cannot rotate. Sorry, it can only translate and rotate the plane. And so how many degree of freedom do you think this is? Anyone want to shout out the answer for planar joint? You can translate in 2 directions, X and Y. You can rotate in 1 Z direction. So it is 3 degrees of freedom, right? So like your mouse, you can do it in the XY direction and you can turn it in theta degree. Okay, but of course mouse, because it's just a point, you're only interested in X and Y. Okay, so screw, okay, let's go to spherical first. Spherical, you can rotate in XYZ direction, but you cannot translate anywhere. Just like your shoulder joint, for example, okay? I can rotate it XYZ direction, but I cannot translate, right? Okay, so that is spherical. And screw is highly interesting, okay? Even though it can rotate and it can translate, but the rotation and the translation are not independent, okay? That means if I rotate by, let's say, 722 degrees, okay? It is moving 2 rounds. it will actually move by 2 units of the pitch, okay? So I cannot control the translation if I control the rotation. They are not independent, okay? They are actually coupled. All right, so I won't go into this DH convention, okay? In the past year, we actually do this because we have 3 hours, but I'm going to just tell you that there's a way you can get a description for the kinematics of your robot using this, what we call Danavik-Heidenberg convention. There are also other ways known as product of exponential, okay? But I'm just going to show you that it is nothing but describing for DH way, it is nothing but assigning the frame like what we have did earlier on. Okay, when we assign the frame to a rigid body, we can describe a rigid body with respect to another rigid body. So now it becomes useful. If I have a joint 1 and I have a joint 2, okay, and I know my joint angle, okay, so I can find the description of my joint 1 to joint 2, all right, and that will form a transformation matrix. So if I have I to I plus 1, that means I can do from 0 to n, okay, 0 to 1, 1 to 2, 2 to 3, all the way to n minus 1 to n, okay, as long as I know all my joint variables, okay. So this helps us to work out this transformation matrix that we need to describe from one frame to another. Okay, so in the slide, you will see the specific steps, but I will not go into detail in today's lecture. Okay, because there will also be other ways like of exponential. But you need to know that in order to work out this, what we call forward kinematics of a robot manipulator arm, you can actually do this. Okay, so we call this forward kinematics analysis. All right, so the first step is just assigning all the frame to all your links. Okay, actually at the position of your joint, but the frame is really attached to a link to describe the link. And then once you have each of these relative relationship, you can eventually get the transformation matrix by multiplying them. Okay, so there's actually an animation here, but in your PDF slide, you may not be able to see this. Okay, so if you are interested, look into this DH convention. Okay, you will find the steps in doing it. All right. So there are also some example in the slides that you can follow. Okay, to make sure that you understand them. Right. Really, your DH convention is just doing 4 steps. Okay, to move from frame I minus 1 to I. Okay, 4 transformation, and you will get 1 homogeneous transformation. Okay, so that allows you to do a forward kinematics. Okay, so forward kinematics, now that I have described so much about it, do you know what is it trying to do? Okay, usually, of course, we will tell the student what is it trying to do before we start telling them how to do it. But now I actually do it the other way around. Okay. So when we talk about forward kinematics, is that we are interested in finding the position and orientation of a particular frame, usually the n effector, with respect to another frame, usually the base frame. Okay, so we are interested in getting our 0 TE. Okay, we are interested in getting this. Okay, let's say I have my body is a base frame and my hand here is my n effector. I want to know my hand with respect to my body. Okay, so if I know all my joint angle, okay, usually we use theta 1, theta 2, or Q1, Q2, all the way to Qn to represent my joint angle. Okay, I can have a function that will tell me the position of my hand with respect to body based on the joint variables. Okay, so the problem of forward kinematics is basically I give you the joint variables, you tell me the coordinate space pose. Okay, as simple as that, right? Meaning if I send this value to the robot, where will the hand be? Okay. So there's one example 2.3 here. You can try it out yourself. Okay, working out the whole DH function where you can do a mapping from your joint variable to your n effector pose. Okay, so basically forward kinematics is nothing but mapping from the joint space to the Cartesian space, Cartesian workspace. Okay, so this example will have numbers that you can try. Right, I will leave you to try it out yourself. All right. Okay, and in fact, you can verify this very simple toy example by using geometry. And so I talked about forward kinematics and what is inverse kinematics. It is actually to do the other way around. Forward kinematic is I give you the joint variables, you tell me the n effector pose. So inverse kinematic is the other way around. If I want my n effector pose to be at certain specific position and orientation, what kind of joint value should I send in to the robot? Okay, that means I tell you the position and orientation of my hand. You tell me what are the angles of my joint. Okay, that is inverse kinematics, right? So it's the other way around. So a lot of time, if you want to solve a actual problem, move a cup, let's say from point A to point B without spilling the water over, this is an inverse kinematics problem. You need to tell the robot what values of joint they should be having in order to have this, fulfill this pose of your n effector. Okay, so again, the same example can be used for inverse kinematics. You can take a look. Okay, and a bit about solvability. For serial manipulator, forward kinematics is guaranteed. You can always have analytical form of forward kinematics. That means if I tell you Q1, Q2 all the way to Qn, you can definitely tell me the position and orientation of my hand. Okay, but the other way around is not true. Okay, if I tell you the position and orientation of my hand, and I want you to tell me what are the joint angles, okay, to get this position or orientation, there is not always a guaranteed solution. Okay, there could be no solution, there could be one unique solution, there could be infinite or more than one unique solution. Okay, we don't know for serial manipulator. Okay, so the solution could be obtained sometime numerically if it is if there is, okay. If not, most of the time you need to use numerical solution. Okay, so before we actually work out the solution, of course, we want to analyze it. There are things like reachability based on the workspace, whether solution is even portable or not. Okay, there are dexterous workspace and reachable workspace. Reachable workspace can reach the position and orientation or not. Dexterous means it can reach, not only reach, but also orientate in different directions or different orientation. Okay. So I will let you go through this. Okay. There are some point of time where there are more than one possible solution. Okay. Something like this. Okay. At the envelope within the workspace. Okay. To get that particular pose, you can have two possible solutions. Okay. And if you think about it, how will you be able to get one unique solution? If this is a workspace of my robot, okay, this yellow envelope define my workspace. Where do you think I will have only unique solution? Okay, we know that anything inside here will have more than one solution, two solutions, right? But is there a place where we only have one unique solution? Anyone want to try? Okay, so for those, anyone want to try? For those who did robotics, you should know there's this concept of singularity. Okay, and it usually happens at the boundary of your workspace. So imagine if you stretch our robot all the way to either boundary, the inner or outer boundary, there will only be one unique solution. Okay, right? Okay, but I won't go into that because that involves a lot more mathematical detail. Okay, the next 10 minutes, I'll very quickly run through this mechanics, finishing the mechanics already, the control and perception. Okay, so this is the whole big part that we have defined for the scope of robotics, and we already covered the main part of mechanics, meaning being able to describe and represent your robot. This is actually half the battle one, okay, when you're designing a robot, everything. The next thing, of course, you need to design the right control scheme, the right planning algorithm, and finally, the intelligence with perception of the environment, okay? So later in the afternoon, if we have a chance, we can actually look at a four-legged robot after the control class, okay? Ask one of the students to bring that over. But a lot of control will be involved in something like this. So in a lot of robotics application, you know that you need to, because our objective is to realize or achieve the desired outcome, we need to have a control scheme that allow us to know what kind of control input to send in to the dynamic system such that it will result in a desired outcome within a specific performance. Okay, a lot more will be discussed in the afternoon on this part. So let's not worry. Okay, this is Boston Dynamics. I'm sure you have seen some of this dancing robot doing robot parkour, all the amazing stunt, acrobatic stunt. But actually behind the glamorous part is a painstaking development process, okay, where you will see a lot of failure situation. Okay, so it's not always so uh, glamorous as you see. Okay, a lot of painful process involved. Okay, so dynamic problem is really when we are concerned about the force. When we talk about kinematics, we don't care about what kind of force should we send in to achieve the motion. But in dynamics, it is actually a mapping between the force and the motion. That means we are interested in the motion and the cause of this motion, right? In order for you to have a motion, acceleration, velocity, and displacement, you will need a force or a torque, right? So in dynamics of robotics, we are interested in finding out this equation and describe the dynamics. That means if I tell you all this motion profile, okay, theta, theta, double dot, and theta dot, you can work out what kind of torque that is required to perform this motion, okay? So that is a dynamic equation. Because this require a lot of discussion, I'm going to just tell you the concept, right? And once you have the dynamics, you can then work out the control system or develop the control system. All right. So the control problem is really like what I say, designing a control system that can tell you what kind of input to send into your system here to achieve the output that you want. Okay. And this part of independent joint control, we will discuss in the afternoon a lot more in detail. Just to tell you in robot, okay, in a robot, when we design a control, we are usually looking at each of these joints independently, okay? But of course, this is less and less true, okay? These days, we are looking at more complicated multiple input, multiple output. Okay, but we can look at this as controlling just a single joint. Okay, so once we can control one joint, we control a lot to achieve what we want for the whole robot. All right. Okay, so that is the big picture. But in control system, we assume that we already know what we want the robot to do. But what kind of action that will lead our robot from a start configuration to a goal configuration is what we call a planning problem. Okay. So in robotic planning, okay, this will kind of close up the look for the whole structure that we are looking at. Okay, is to tell or send in some command. The proper terminology is actually trajectory reference. Okay, in control terminology, we call it reference or set point to the control system, to our controller. Okay. So control problem, if you want to simplify it, it is nothing but formulating this set of action to solve a problem or achieve a goal. Okay, so there are a lot of problems like imagine some of them are just mathematical, okay, like moving a sofa across the corner, okay, what are the dimensions that or the constraint that you should consider, and moving a piano one initial position to a final pose, okay, in a cluttered environment, you need to come up with the right sequence of actions, right? This is very common for those who already got your driving license. It's not always so simple to do a parallel parking, right? Okay, you want to do something like this because this is non-holonomic. There are some constraints. You cannot just shift the car, translate the car inwards like this. You need to get to a certain path to get it. Okay, not like you can use 隔山打牛 and just hit I into the position. You need to apply certain path in order to reach from this initial state to a final state. The same thing for robot, okay? You need to plan the right action for the robot to take. Okay, let's say there's an obstacle, like someone's face is here. Okay, you want the robot to move from initial position to grab the cup. You need to make sure that the robot doesn't hit the person. Okay, so you need to come out with a sequence of action considering the constraint and condition. All right, the same as the non-holonomic condition that we see in parallel parking. Okay, so there are planning, path planning, motion planning. Path planning meaning we don't care about the time you take. It's just a geometrical shape, the route that you should take. Okay, so in a parallel parking, you can take 2 minutes, you can take 2 hours, 2 days, it's fine if you are doing just path planning. But if you are doing motion planning, you need to make sure that the car is at certain point at certain time. So it's a trajectory profile. Okay, so the difference between trajectory and path is that path is just a geometrical path, a geometrical representation without time consideration. Okay, motion planning, we consider the time. All right, task planning is just getting from one state to another so that you complete certain tasks, like in a surgical intervention in this case. We want the burning or the treatment to cover a certain region. We need to perform a certain sequence of actions as task planning. Okay, so in the context of robotics, of course, it is important, right? This famous professor actually says something like, it is necessary because by definition itself, robot is designed to accomplish tasks that move in the real physical world. Okay, so there are a lot of examples. This four-legged robot, I think I will show you later on in the afternoon as well. So I won't go into detail about this. Okay, this involve a lot of planning and in fact perception, understanding of the sound. Okay, right. So to put them all into context, we have, let's say in a scenario like this. Okay, so in the interest of time, I will leave you to look at this yourself. Okay, because in the past we actually cover a few more planning algorithm, but in this case, I just want you to be able to fit this concept into the whole picture of robotics. So there are lists of this, basically the 2 steps. You need to kind of formulate a problem, right? And the second step is to design the algorithm, right? Telling the robot to take what kind of step. And mathematically, there's a way of describing this problem in different space, okay? Either in your task space, workspace, or your configuration space, okay? Don't worry, maybe some of the illustration, we can also do it in the afternoon, right? Because I'm kind of running out of time. Supposed to end at 10:30, right? Okay, so just to let you know that there are some of this planning involved, right? So finally, to close out the loop, okay, we will have what we call perception. Okay, it's the same as sensing for control, but at a higher level in understanding the environment by looking at images. Okay, so robot, of course, there are many different ways of perceiving the environment, not just vision. But vision is one of the most common way to interact with the environment. you see, because it's long range, etc. Okay, so of course, beyond the scope, you will see more sophisticated stuff if you ever pursue the track of robotics. Okay, there are higher level intelligence involved, but in this lecture, we're just going to end to this part here, where we look at the perception part. Okay, the idea here is that there's actually a lot of things happening in our brain when we look at an image. Okay, it's not always what we see. If you look at this is, even though not the first time I've seen this, but every time I see it's like a lot of wavy lines. But actually, they are all parallel lines. Okay, I didn't do anything but just shifting it. So your brain is telling you something different. It is actually going through a lot of process when you look at this image. Okay, a very quick experiment, mental experiment. Okay, which area do you think is larger? And some of you might have seen this. Who think area A is larger? Who think B is larger? Okay, or some of you think. So if you didn't raise your hand, you are also right because they are actually the same area. Okay, I didn't do anything but just rotate and transform. Okay, they are actually the same thing, but our brain kind of process the information here to tell us that there are different areas. Maybe by looking at the legs, the aspect ratio is different. So we think that if this is a 3D image, okay, A is something narrow and longer, B is something broader, okay, more regular. But just looking at the image geometrically, they are the same area, okay? So it's not always easy for a robot to understand the image when we give it to them, okay? I'm supposed to end at 10:30. Okay, very quickly, I will take another 5 more minutes. Okay, so if you look at something like this, to make sense of the image, it may not be very easy, right? If you look at this, okay, maybe now this is an old picture. A lot of us, we have cameras on our vehicle, so we may have seen something like this. So your brain is able to tell you what is happening. It's not a giant monkey trying to attack the vehicle, right? It's actually because the monkey is very near to the camera on the car. It's actually, the monkey is just on the windscreen, and then the front car, the car in front is actually further away from the camera. So it looks as if the monkey is like giant monkey on a smaller car, right? But this is because you don't have the depth information, all right? And what about the one on the right? Is there really a giant bird and a small man? Not true, right? If your brain see this often, your common sense will give you a precondition that the pigeon cannot be larger than a human. Okay, so actually the bird is just standing in front of the window and the man is outside the window or out in the road, so it appears smaller. So we need to have this kind of information, this kind of perception for a robot to be able to understand the surrounding. So just feeding them images may not be sufficient, okay? Because our brain is actually doing a lot of processing, even for a human. Okay, but I won't go too much into detail for now. Some of these are very common industrial situation. This video is not playing correctly, but actually there's a screen here to show what the camera is capturing, okay? Basically, the robot can collaborate with each other, but they need to feed all this information. So the camera is actually the randomly assorted pieces, and this part is packing them into order, and then you use a manipulator that transport them from one belt to another. Okay. So in research, we also have similar, like for microscope, we can use the image to tell our micro manipulator robot to do certain tasks that we want. Okay. So this vision part will tie on, kind of like close up the loop. Some example that we have that can take a robotic micro manipulation. See all 3 axes moving together in 3D space. They are moving in 3D space, but microscope is only a 2D image. So there are a lot of challenges that we need to overcome in giving the robot sufficient information about the surrounding. Okay, so I won't go too much into detail. Okay, I'm reaching the end with just some very interesting thought when you are designing your robot to have this ability to understand the environment. You can actually look at many of different nature capability in these living creatures, like the eagle actually have very strong stereoscopic capability. When it's trying to get a prey, it will kind of, it's like 3D constructing the scene. You will fly over the sky and kind of gather enough depth information before they strike. Okay, and the bat or even dolphins or some fishes, they have this echolocation capability. They can use sound wave. Maybe this is not really vision, okay? Or we actually consider this vision because they actually visualize the sound wave, right? And something not so common is defocusing. Okay, you can make use of the focusing plane, moving the focusing plane to tell you the depth information. We use that for the microscope robot. Okay, so we can have all this designed for our robot. A robot can have all this capability, not just using a single camera or using more than one camera or infrared, etc. But we can have a whole range of sensor that can help us perceive the environment. Okay, things like the LiDAR that you see here. Okay, is like echolocation, and the infrared, like the snake, can sense sound motion very well. Okay. All right. So with that, summarizing what we have learned, we covered robot mechanics, design and control, but control a lot more in this afternoon's lecture, and then a bit on the perception, so that we, the important thing here is actually familiarizing with the fundamentals. Okay, so next time if you are pursuing the track of robotics, or you need to apply robotic concept on some of your project involving smart cities, etc. Okay, you need to understand this knowledge structure, how you build them, and how you apply the fundamentals to achieve what you would like to have. Okay, and of course we applied. We look at some of the applied topics and example in the application. All right. So that will be all for this morning's lecture. Okay, and of course, this afternoon we will have lectures on control system, and we will actually go slightly deeper into control system design. All right. Okay. I will see you this afternoon. Right. Thank you so much.